Good morning, everyone, or good afternoon, depending on where you are. I would like to welcome you all to this event. As you know, it's not the first and not the last in a series of events that celebrate books that built the general relativity community the way we know it now. And the book that we're celebrating today is General Relativity by Bob Wald. Thanks to Bob for agreeing to participate today, and thanks to David Garfinkle, who was involved in ways that I will explain in the writing of this book. We have already celebrated two books, MTW, Misner, Thorne, and Wheeler, and the large-scale structural space-time by Hawking and Ellis. And I will get out of the way very quickly here. I just want to give you a very brief introduction to the speakers that we have. So let me share my screen very briefly. I prepared two slides. I hope you can see the first slide now. Slideshow play from start. Can you see it full screen? Is it working? So this slide is just to introduce the first of our two speakers today. David Garfinkle. David, you probably know him. He did research on many different topics in general relativity using both analytical tools and numerical tools. He worked in particular on space-time singularities, black holes. He's an expert on gravitational wave memory. He worked on critical gravitational collapse, cosmic strings, and many other topics, including relativistic astrophysics and so on. He got his bachelor degree from Princeton University in 1980, and then he got his PhD from the University of Chicago, where his advisor was Bob, and that's why the connection, as he will explain later on today. After that, he was a postdoc at Washington University in St. Louis, where I was also a postdoc some years later, and at the University of Florida, and at University of California in Santa Barbara. Then in 1991, he got a professorship at Oakland University, where he has been since then, and he is now a distinguished professor of physics there. David wrote two books, one with his brother. Is that right, David?
Actually, both with my brother.
Both.
They're both popularizations, one on physics and one on math.
Right. And over 150 papers. He has served on the editorial board of many different journals, including Physical Review D, Classical and Quantum Gravity, American Journal of Physics, International Journal of Modern Physics D. And I want to list some of his honors and leadership roles. He has served as secretary-treasurer of the topical group in gravitation before it became the Division of Gravitational Physics. And he was on the chair line of the topical group in gravitation between 2006 and 2009. One thing that I particularly appreciate is that he has been the editor of Matters of Gravity for a very, very long time, and that was service to a community that we should all be thankful for. In 2007, he became an outstanding referee for the American Physical Society, and he was chosen in the first group of referees, which means he was doing, again, a lot of hidden service for all of us when it wasn't cool. And he became an APS fellow in 2008. He is now serving as secretary-treasurer of the International Society on General Relativity and Gravitation. And right now he's serving as the APS April meeting chair in representation of the Division of Gravitational Physics. That's all I had to say to introduce David, and I'll let you take over for now.
Okay, can you hear me?
Yep.
Okay, let me try to share my screen then. Let's see. Okay, can you see that?
It's working.
Okay, great. So thanks very much, Emanuele, for that very generous introduction. And I should say that for that last item about APS meeting chair, if anyone in the audience has any ideas for plenary talks that should be given at the upcoming APS meeting, you should email them to me. Okay, so I am very honored to be the opening act in this celebration. So let's go ahead and get started. Okay, so we are celebrating the 40th anniversary of the publication of General Relativity by Bob Wald. And I have here on this slide 2 copies of this book. So the one on the left was given to me by Bob 40 years ago. And as you can see, it's a little bit the worse for wear. So I also have another copy shown on the right. And it's actually very helpful to have 2 copies because for those of us still using physical books, since we do some work at home and some work at the office, this way you can have 1 copy in each place. And, you know, that way, wherever you are, you always have a copy of Bob Wald's book to use as a reference. I should mention that even though the title of this book is General Relativity, hardly anyone actually refers to it as General Relativity. Almost everybody will say either Bob Wald's book or Wald's book, or most often of all, just Wald. That's sort of how familiar we all are with it. Okay, so when I was Bob's grad student, he taught me a bunch of things about giving talks. And one thing is that you should, you know, state at the beginning the stuff you're going to say. So here's my outline. I'm going to start by explaining how I first became acquainted with Bob and his book. And then I'm going to show you a couple of phrases from the blurbs in the book, and I will discuss those. And then I will discuss a couple of phrases from the introduction, and then say a few words about the structure and content of the book, and then I'll conclude. And it's a good thing that I'm giving the first talk, because that way, if I say anything egregiously wrong, Bob can correct me in his talk. Okay, so my encounter with Bob and his book. I actually took a general relativity course as an undergraduate, and it was taught by Terry Tomboulis, and the textbook we used was Misner, Thorne, and Wheeler, and I did not understand a word of it. I thought it was a fascinating subject, but at the end of the course, I had no more understanding of it than I had at the beginning of the course. But when I became a graduate student, my sort of lack of knowledge of general relativity didn't matter at first, because I was an experimental high energy physicist. And one of the things that I did was to participate in running an experiment at Fermilab. And one of the things that that experiment taught me beyond any doubt is that I was meant to be a theorist. And oddly enough, I'm not the first person to come to that conclusion, because it turns out that Katie Fries was also a graduate student on that experiment, and she also was convinced by that experiment that she should become a theorist. So I'm followed in her footsteps. One of the things that happens when you're running an experiment is that the experiment runs 24 hours a day. And so you sort of take an 8-hour shift, and you tend to the experiment in that amount of time. And there's not much to do in those 8 hours, because basically you're just checking to make sure that, you know, data is being taken and that nothing is broken down. And so there's sort of a lot of free time. And one of the things I decided to do with that free time was to see if I could, you know, learn a little bit of general relativity. So it turns out that, as many of you know, Landau and Lifshitz's classical theory of fields covers all of general relativity in the last 100 pages of their book that's ostensibly on electromagnetism. And so I read that, during some, midnight to 8 in the morning shifts at Fermilab. And at the end of reading those 100 pages, all of a sudden, things were starting to make sense. So when I decided to jump ship and become a theorist, I talked to various people, including Bob, and I asked to join his group. And so he agreed to take me on as a graduate student on a probationary basis. That is, to see if things worked out. Now, I mention this because that opens the possibility that Bob has not made up his mind about whether things work out or not. I'll leave it to you to decide which way you think it goes. But in any case, in hanging out in the Chicago Relativity group, one of the things that became clear to me was that their approach to the subject was very different from that of Landau and Lifshitz. Landau and Lifshitz did everything in coordinates, and the Chicago style is to be allergic to coordinates and do everything geometrically. And so I asked Bob, can you recommend a book that I can read that can teach me this geometric way of doing relativity that you guys use? And he said, funny that you should say that, because I'm writing such a book. And he handed me a set of manuscript pages, about this thick or so. And he said, go ahead and read this book and ask me if you have any questions. And this was really great because not only is it a fabulous book, but Bob himself is very dedicated to making things clear. And so, when there was something I didn't understand, I could actually, talk to him and say, please explain this to me, and he would. And, this went on for a while. But every now and then, when I would ask him a question, he would say, oh, wait, you don't understand that because it's wrong. I better fix that before the book is published. And it turned out that this was a very bad strategy on my part, because after, enough times of this, he, said to me, you seem to be very good at finding mistakes in my book. So why don't you check all of the equations in the book and let me know of all of the mistakes. And so I did that, although I got a reprieve because it turned out that I asked if I could be excused from checking the equations in chapter 13 on spinors, and Bob agreed that, okay, I didn't have to do that. So this was a nice introduction to the subject, because checking equations doesn't mean that you, sort of look somewhere else to see if that equation matches what you find somewhere else. It means that every single equation is true either from first principles or from deriving things from the other equations. And so one of the things that I absorbed from this, which is a staple of Bob's style, is that we look for clarity in the foundations of physics. General relativity is a foundational theory, and everything, no matter how abstruse or how complicated, is supposed to make sense. Okay, so that's a summary. Now, I want to turn to a couple of phrases from the blurbs. So when you publish a book, your publisher always wants you to get, some prestigious people to write some nice things about your book. Bob, as a sort of classic overachiever, got a blurb from Chandrasekhar and a blurb from Penrose. And I want to read you a couple of phrases from each of these blurbs. So Chandra says, Wald's book is clearly the first textbook on general relativity with a totally modern point of view. And Penrose says, General Relativity is an excellent book, and it should fill a gap in the literature that has opened up over the past several years for a comprehensive and reasonably up-to-date graduate text in general relativity. Now, you might think, that this is an odd thing for me to highlight in a talk about a book that's 40 years old, right? I mean, something that was modern 40 years ago is surely not modern in the sense of the latest stuff coming out of the fields now. But I do want to emphasize this because modern 40 years ago meant that it contained the geometric insights of the global structure program of relativity about space-time and particularly about black holes. And especially now, it's very important to preserve those insights. And let me sort of digress a little bit to say why. So one of the things that we've seen in the last several years is that in response to the wonderful data coming from the gravitational experiments, the field has shifted towards gravitational wave astrophysics and gravitational wave phenomenology. And this is entirely appropriate, but it also risks leaving behind some of these foundational insights. Furthermore, a lot of the foundational work now is being done by people whose training is in particle physics and string theory, and they have a very different attitude towards the foundations of physics. So we're in danger of losing some of these insights, and one of the best ways to maintain this is for as many people as possible to read Bob's book. All right, now I want to turn to a few phrases from the introduction. So these are things that Bob says in the couple of pages of introduction to the book. So one of the things that he notes is that this is supposed to be both a text for graduate students and a reference book for researchers. And this says something about the structure of the book because it comes in two parts, which are labeled fundamentals and advanced topics. And I'll say a little bit more about that later. And roughly speaking, the fundamental stuff is supposed to be the textbook part, and the advanced topic is supposed to be the reference book for researchers. Although I have to tell you that in using the book as a reference work, I'm just as likely to look up stuff from the first few chapters or from the mathematical appendices as I am to look up anything in the advanced topics. Another phrase from the introduction that I want to highlight is the statement, problems are given at the end of each chapter. And then he goes on to say a few other things and to end with none of the problems are, in my opinion, inordinately difficult, i.e., I think I can solve them. So this phrase is characteristic of Bob in two ways, because on the one hand, Bob is always very precise. And so if he hasn't actually solved the problem yet, then he doesn't know for sure that he can solve it. So, it's appropriate to say, I think I can solve them. On the other hand, this is also an extraordinarily effective way to intimidate the students and everyone else, because you sort of look at that and you say, wow, problems that Bob doesn't even know if he can solve. These must be really, really hard problems. Okay, another piece of the introduction that I want to highlight is the phrase, the influence of Robert Garrow should be apparent to readers familiar with his viewpoints on general relativity. And I'll say a little bit later about, what some of those viewpoints are. But in particular, the two Bobs together have developed a Chicago style of relativity, which emphasizes the importance of general relativity as a fundamental theory of physics and emphasizes thinking clearly and mathematically about things. And since Garrosh did not choose to write a relativity textbook, this book is essentially the quintessential Chicago-style relativity book. And then finally, another phrase from the introduction, where he says, additional thanks are due to David Garfinkle for checking most of the equations. I include this phrase both to, again, outrageously brag about that, but also because of something that's missing from the introduction, because most authors, when they write a phrase like that, immediately follow it with a phrase that says, any remaining mistakes in this book are my sole responsibility, and Bob did not choose to do that, which leaves open the possibility that maybe I'm responsible for any remaining mistakes. And if so, if you find some mistakes, you should let me know. Okay, so now let me go on and say a little bit about the structure and the properties of the book. As you all know, Bob is a very mathematical physicist. And in particular, one of the things that we know is that physicists do calculations and mathematicians prove theorems. Bob is one of those few people who is versatile enough to do both. To a certain extent, this is reflected in the sort of notation used in the book. So in particular, most physicists, when they write tensors, they write everything in terms of coordinate components. Most mathematicians, when they write tensors, they just, write some letter for the tensor with, if you're lucky, maybe a couple of parentheses and commas to tell you what kind of tensor it is. The abstract index notation basically uses indices, but not as these are things that are coordinate components. Rather, they're just labels like the arrow on a vector to tell you what kind of tensor it is. So the notion is that we're dealing with geometric objects, but we want to deal with them in a way that allows us to calculate things. And this is important because even now we have, a bunch of crazy people saying things like, well, the time coordinate goes to infinity at the Schwarzschild horizon, so you can never actually get inside a black hole. And that's, of course, completely ridiculous, but it's good to have the geometric point of view to remind us of why it's ridiculous, right? A black hole is some space-time, and Schwarzschild T is some coordinate that goes bad on the horizon, and well, that's too bad for Schwarzschild T, but it tells us nothing about the black hole. The book also uses a signature of minus plus plus plus, except for the spinor chapter. For spinners, it's better to use the other signature. And this is also helpful because, the fewer minus signs you have to worry about, the easier it is to do calculations. But in addition, thinking of space-time as geometry, if I have a metric with the signature minus plus plus plus, and I restrict it to a space-like surface, now I get a Riemannian metric that gives the geometry of that surface. Okay, so even though the book is divided into fundamentals and advanced topics, the basic mathematical tools of the theory are really developed in the first 4 chapters, and everything else, including chapters 5 and 6, which are in the fundamentals part of the book, are really applications, right? So chapter 5 is an application to cosmology, chapter 6 is an application to the Schwarzschild metric. And then the advanced topics are treated in the second part of the book. Another quintessential Chicago-style part of the book is that coordinates are never introduced at the beginning. So a lot of textbooks will say, oh, we consider a metric of the following form, and then they'll write down a line element. For Bob, you always start with symmetry groups, and you use those symmetry groups to derive, in some cases prove, that therefore there is a coordinate system with the following properties. Okay, so now let me say a little bit about the advanced topics. Chapter 7 on exact solutions is not exactly an advanced topic. I don't think it's necessarily much more advanced than chapters 5 or 6, but you got to divide the book some way, and in some sense exact solutions are sort of a specialized topic, whereas everyone should know about Schwarzschild and Robertson Walker. But then he goes on to talk about global structure methods, and that really is an advanced topic. And in fact, it's quite a challenging topic. But it turns out that even though the topic in this book of global structure is quite challenging, it's less challenging than in Hawking and Ellis. Roughly speaking, because Hawking and Ellis is a monograph, whereas Bob's book is a textbook. So there's sort of more of an obligation to explain things in a way that students can understand. And in fact, I think Bob is both happy and mildly embarrassed that sometimes when people will refer to some singularity theorem that's shown in Hawking and Ellis, that they'll actually refer to Bob Wald's book rather than referring to Hawking and Ellis, because in Wald's book they found an explanation that they could understand. The initial value formulation, at least in capsule summary, is presented, although a lot of stuff on the initial value formulation has been done in the years since, in particular by Christodoulou and his collaborators and students. There's also a presentation of asymptotic flatness, and then I want to turn to the stuff in the last few chapters. So in keeping with the fact that I didn't check anything on spinners, I'm not going to say much about that. So the last 3 chapters talk about black holes, and then spinners, and then quantum gravity. The treatment of black holes is kind of funny, because on the one hand, a black hole is a geometric object. It's an asymptotically flat space-time in which the past of future null infinity is not the whole space-time. But on the other hand, vacuum black holes settle down to the Kerr metric. So what that means is that you can actually learn a whole bunch just by examining the properties of the Kerr metric. And then the final chapter is about, it's titled Quantum Effects in Strong Gravitational Fields. And there is some discussion of quantum gravity, but most of the chapter is about quantum fields in curved spacetime. And this is something which is Bob's main specialty in research, and something that he has expanded in subsequent books. But I want to say a little bit about sort of the flavor of the subject. On the one hand, quantum fields in curved spacetime is sort of an odd subject for someone with Bob's style, right? Because Bob is very careful to get everything exactly right. And notoriously, plain old ordinary flat space quantum field theory is a subject in which there are all sorts of inconsistencies that pop up as various infinities, which have to be swept under the rug in an ad hoc procedure that sort of seems to work. So you would think that trying to generalize the methods of quantum field theory to include general relativity would be a subject that someone as careful and exact as Bob would shy away from. But it turns out that there is a loophole. There is a nice formalism first developed by Whiteman for how to talk about quantum fields in a completely rigorous way. And the basic idea is that a quantum field is supposed to be an operator value distribution. And you can do lots of stuff with distributions, but one of the things that's hard to do with them is multiply them. And so what that means is that rigorous quantum field theory works a lot better when you're doing free field theory than when you're doing interacting field theory. And the nice thing about quantum fields in curved space-time is that even free field theory has interesting properties because free field theory just means that the quantum field is not interacting with itself. You can put in lots of stuff about how it interacts with the space-time. So I think, Bob sort of saw a chance to take this sort of new at the time field and actually make some rigorous mathematical sense of it. And he's been at it ever since. And that work has a lot of staying power. For example, the recent work by Bob and his students and collaborators on black holes and horizons, decohering everything in sight, is an example of the fact that this subject is still very interesting to this day. Okay, so now I want to conclude. And okay, so actually, sorry, before I do that, let me say a little bit about what the book doesn't contain. The book is about the foundations of general relativity. So general relativity considered from the point of view of, what does this say as a fundamental theory of space-time and gravity? What that means is that it does not contain detailed treatments of relativistic astrophysics. There's some stuff about relativistic astrophysics in there, but just the sort of bare bones. And similarly, there are no detailed treatments of relativistic cosmology. There is some stuff about cosmology there, but just enough to, consider Robertson-Walker as a sort of interesting space-time, and here's some stuff that happens in there. Similarly, there's no detailed treatments of the post-Newtonian approximation, there's nothing about numerical relativity. There's all sorts of stuff that are topics in relativity that you should go to other textbooks for. But what this textbook does is to give the foundations of general relativity and to do it in a mathematical, precise, and geometric way. Okay, so now I want to turn to my conclusion. And before I do that, I want to mention that one of the things that Bob told me about giving talks is that your talk should always have a punchline. And then he went on to say, the only thing that your audience is going to remember about your whole talk is your punchline. So you better have a punchline. Here's my punchline. If you want a deep and thorough understanding of general relativity, then the book General Relativity by Bob Wald is the book that you should read. So thank you very much for your attention, and that's all I have to say.
Thank you, David. I don't know if we want to take a question or two before we move on to Bob.
Either way, whichever way you want to do it is fine with me.
Okay. If I don't see anyone raising their hands in the next minute, I will just very briefly introduce Bob, although I don't think I really need to do that, but I'll put on my one slide over here. Well, much of what I had to say was already said by David, but as you all know, Bob Wald is one of the most eminent relativists. He did lots of research on black holes, in particular on black hole thermodynamics, introducing some key ideas like the Wald entropy. He worked a lot, especially in the last few years, on topics like gravitation-radiation reaction. As David said, he made fundamental contributions to axiomatic quantum field theory in curved space-time. He's been interested in many fundamental issues in cosmology, and very recently, in part, thanks or because of Dan Holtz, I don't know if you want to blame him or thank him for this, he joined LIGO. Bob got his bachelor degree from Columbia University in 1968. He got a PhD from Princeton in 1972, where his advisor was John Wheeler. And after his PhD, he had a research assistant position, or I don't know what you want to call it, a postdoc, first at the University of Maryland and then in Chicago, where he became a professor in 1976. And now he's the Charles H. Swift Distinguished Service Professor in Chicago. He published many papers. I counted about 170 on Inspire, and several books, in fact, not just the one that we're celebrating today. His first book is called Space, Time, and Gravity, and it's actually a popular book similar to the ones that David wrote. Then he wrote General Relativity in 1984. And after that, he wrote a very slim book on quantum field theory in curved space-time and black hole thermodynamics, which is slim but very dense. And in 1998, I would also like to point out he was the editor of a volume that is called Black Holes and Relativistic Stars, that was put together after a symposium in honor of Chandra. And I know that book because I read several of the contributions in that book. My former PhD advisor, Valeria Ferrari, was at that symposium back in 1998. And very recently, Bob put together a book on advanced classical ENM. So I would like to advertise it here because it's a book on ENM that, does what Bob does, but for classical ENM, and it's an excellent textbook. He received several honors. He became an APS fellow in 1996. He's an excellent teacher, as you all know if you have read the book, and he got a teaching award graduate teaching award from the University of Chicago in 1997. He has served on the advisory board of the Kavli Institute of Theoretical Physics between 1998 and 2001, and is a fellow of several societies, including the American Academy of Arts and Sciences and the National Academy of Sciences. Relatively recently, he also got the Einstein Prize from the American Physical Society. You probably knew all of this, but I had to say it, and I'll stop sharing, and I'll let Bob take over and tell us more about the book. I understand that he doesn't have any slides, so I welcome everyone to raise their hands and ask questions. Bob, I don't know if you want to keep track of that, but if there are questions, I will just let you know, and let's try to make this into a lively conversation if we can.
Yeah. Okay. Everyone, I hope, can hear me. Yeah, I thought I would just make a few informal remarks. I mean, that should give some idea of what was going through my mind as I, as I decided to write the book and as I wrote the book. And I thought it would be best to do that in a kind of my own questions and answers format that I gave in the abstract. So I'll do that, and then when I'm done, I'd be very happy to throw things open to questions not asked by me. So I am asked a lot of questions about the book, when I meet students, colleagues, and so on. And one of the questions I'm often asked is why I wrote the book. And that isn't it isn't so obvious because there were other quite good books around at the time, well, before I started writing it. So I just thought the three books that were dominating the landscape by the mid 1970s was Weinberg's Gravitation and Cosmology, and of course Misner, Thorne, and Wheeler, and then the Hawking and Ellis monograph. Of course, there were older books. I mean, Landau Lifshitz, Singh's book, and so on. But those were, well, in a kind of older mathematical style. There were some newer books too, but I think that the three that I mentioned, I think really were the dominant books. Now, if Weinberg's book were the only one around, I would have very good motivation for writing my book. I mean, Weinberg's book has excellent discussions of cosmology. I mean, those, of course, are rather out of date by now, but were not, and were really excellent at the time he wrote the book. And it has a lot of detailed calculations of things that are quite remarkable and quite useful. But the attitude expressed in the book, which, well, maybe was even more extreme and certainly more explicit than was generally prevailing, particularly in the particle physics community at the time, was, I mean, I think looking back on it, even I feel that way even more so now than then, really rather remarkable. I'll just quote a sentence from the short section of Weinberg's book entitled The Geometric Analogy. And he says other things in this too, but this is probably the most representative. The geometric interpretation of the theory of gravitation has dwindled to a mere analogy, which lingers in our language in terms like metric, affine connection, curvature, but is otherwise not very useful. So that was sort of part of the landscape as I was writing this, that the book, and particularly that section, always makes me think that the Earth is flat, except for some geodesic corrections that I can show you how to calculate with Christoffel symbols, and except for some global topological considerations which are beyond the scope of what I want to tell you about now. Anyway. Okay, the two other books, I mean, were Misner, Thorne, and Wheeler, and Hawking and Ellis. Misner, Thorne, and Wheeler is an excellent book, and that does have the fully modern kind of geometric perspective. So it wasn't to get a book out there that was countering Weinberg's or whatever that was in any way really part of the motivation. The problem I had with Misner, Thorne, and Wheeler, I mean, problem to the extent that I was motivated to write a book of my own, is their treatment of mathematical topics, which is all, they definitely don't say anything wrong. It'd be hard to do that, particularly with, well, Misner and Thorne writing it, and Wheeler as well. But the treatment is extremely roundabout, and it's very hard to find the definitions of things, the mathematical precise definitions of things, and to find clear proofs. Well, in some cases, topics are treated in boxes, and that's usually fine. But the things that are not in boxes, I often got rather frustrated with. And just one quick anecdote on that, which might give a little bit of the flavor of, again, what was going through my mind. I should say I learned the most of what I knew at the time of the mathematics of general relativity from a course taught by Charles Misner at Princeton in 1969. That's where I first learned general relativity. And as I say, I learned it from Misner. I then, a few years later, 72 to 74, was a postdoc at University of Maryland. And sometime during the 73, 74 academic year, Misner was teaching relativity, but he was out of town and he asked me to take over the class. And the Misner, Thorne, and Wheeler textbook had just been published. So of course that was being used as the text. And he told me to, you know, what sections of the book he wanted to cover, which was on curvature. And I went through those sections and found them really confusing and, you know, felt it really would be better to just start with the definition of curvature in terms of failure of derivative operators to commute. And then after that, you know, you could go on and give other interpretations, say what you like about it, but it was more being sort of talked about first and kind of not really kind of clearly defined. So when Misner came back, I confronted him on this and, you know, said, why didn't you just give the mathematical definition and, you know, then the discussion later? And I said something like that, but I very distinctly remember Misner's reply, which was, I couldn't agree with you more. I got outvoted. So anyway, the other book on the landscape was the Hawking and Ellis monograph. And that is a truly spectacular book. I mean, it is right on target, precise, has an enormous amount in it and covered at a, you know, really deep level and high level. So the problem with the book, of course, is it is not very pedagogical. And you really can't read it unless you already have a rather deep knowledge of general relativity. So what I had in mind then in kind of the late 1970s, as I was deciding to write a book, is something that would be useful for mathematically minded graduate students trying to learn general relativity and perhaps having the same frustrations of learning the mathematical parts from Misner, Thorne, and Wheeler. I think that, you know, the physical discussion and so on in Misner, Thorne, and Wheeler was something that I would not try to compete with or try to reproduce, and I think, you know, is extremely useful for learning for most students. But for the mathematically minded ones, having some, you know, this is what the definition is, here's property one of this that you prove this way, and here's other things, having it done that way. You know, after going through my book, people would be equipped to read Hawking and Ellis. Well, I reproduced a lot of what's in Hawking and Ellis, so they only a few, maybe even more advanced things would be, you know, required to. Well, I refer to Hawking and Ellis for some of the proofs of the very technical things, so you can't do without it. But anyway, that's what I had in mind. I did not envision at all that it would be widely used as a text. What I envisioned was Misner, Thorne, and Wheeler would completely dominate the market on that for the GR-oriented people, for the particle physics-oriented courses. Weinberg would dominate the market, and I wouldn't be even a competitor. But for the mathematically minded students in that class using Misner, Thorne, and Wheeler as a text, my book might be useful supplemental reading. So in fact, I mean, when I discussed publishing it with University of Chicago Press, the main issue I had in mind was to keep the price down, because I didn't envision this being used as a text. People would use it for supplemental reading, and if the price was as high as a typical text, they probably wouldn't buy it. So that's the sort of thing I had in mind. I mean, I also had in mind it would be used as a reference book for people seriously into doing research in general relativity. So I had two actually distinct motivations in writing the book. I mean, that were really both very clear in my mind. One is I did, as I've described at length now, I did see a need for a book of the sort that I wrote, but at least an equally strong motivation for me was that I really wanted to get a complete grip on a lot of, well, mostly the material that's in the part 2 of advanced topics that David talked about. You know, I pretty much knew the arguments in the singularity theorems, but I was very hazy about a lot of ideas at null infinity, and even more hazy about things having to do with spinors. And I thought writing, I mean, I knew enough about all these things to know the lay of the land, but I didn't know a lot of the details. And I thought this would really be good for me to sit down and work things out and get the logic straight, get the definitions straight. So that was in fact an equally strong motivation in my writing it. Another question I get asked maybe even more often than why I wrote the book is, how long did it take me to write the book? And that was actually remarkably short. I thought of writing the book, well, pretty much immediately after I had written this Space-Time and Gravity semi-popular book that was mentioned by David and Emanuele. That book was based on some lectures open to the public that I had given as a postdoc. And it only, with all that organized, it only took me a couple of months to literally to write that book. And it was a overall very positive experience. And I was very happy with the outcome of that. So with that kind of as a background, as I was, you know, teaching general relativity for a couple of years, I thought of writing, you know, and I had very good notes and had the subject very well organized, corresponding to what became the first 6 chapters of my book. I thought it would be good to write a book on that. And in the late 70s, I wrote up, you know, sort of drafts of what became chapters 2 and 3. But then, I mean, this was going to take a long time. I had other things I was doing, and I kind of just put the project aside for a while. And it was in the spring of 1980 that I made the serious decision to take it up again and really write the book. So I had written effectively several chapters before then, but then I started writing the book in earnest. One might ask what made me decide at that point to do it. Well, there were perhaps a number of factors, but my getting tenure was probably a big factor in terms of deciding I'm just going to go ahead and do this now. So once I had if you consider the spring of 1980 as the start, I finished the complete draft and finished it in a rather polished form sometime, I think, in the late autumn of 1982. So I really was working on the book for 2.5 years, but that was not the only thing I was doing during that period. For example, my collaboration with Bill Unruh started then, and we wrote our paper on lowering boxes into black holes and how you don't violate the generalized second law. I put aside the book for a couple of months to, finish that project and so on. But towards the end, I don't understand how, and my current collaborators, I'm sure, even understand less how I would be writing things so fast, since they're always waiting for me to finish drafts now and turn them back and so on. But I do remember that the last 3 chapters, chapter 12 on black holes, chapter 13 on spinners, and the chapter 14 on quantum effects, I wrote each of those chapters in 1 month. And I didn't know all that. I knew a fair amount about black holes, and I knew a fair amount about quantum field theory and curved space-time. But there was a lot of stuff about spinners that I had to learn as I was writing that. So after I turned in the manuscript, I mean, there were months of polishing and making minor revisions. And I think that's also when David checked all the equations and that sort of thing. So, it was not until exactly 40 years ago, sometime in the spring of 1984, that the book actually came out. So my expectations for the book, as I've already said, was I thought it would play a role as supplemental reading in courses, in GR courses, and would be used as a reference for researchers. But I really did not expect it would be widely used as a text. I mean, I would use it, and I could probably think of another 6 people who might use it, but I really did not envision that for 40 years it would be often adopted as a textbook. In terms of, so that certainly surprised me in terms of reaction to the book, but the kind of thing that by far surprised me the most is maybe best encapsulated by the following, well, again, little anecdote. So first of all, I didn't really even envision this book selling internationally. I mean, that was kind of out of my mind. So it's hard for me to imagine how I would have pictured the following, back in 1984 when the book came out. In autumn of 2019, I was in Sao Paulo, Brazil, and I gave a seminar at the ICPT Saphir there. That was pretty well attended, maybe 80, 90 people in the audience. I don't remember. Okay, what I could not possibly have imagined when I wrote the book is that at the end of my lecture, when I was standing around, and of course, very often a few people will come up with some extra questions, I had a lineup of 20 to 25 people, each carrying a copy of my book and asking me to sign it. Okay, so that is something that I absolutely could not have imagined. And that, isn't a totally isolated incident. I mean, especially internationally when I give talks. Finally, I am not intending to write a second edition for, well, quite a number of reasons. I mean, well, I guess when I asked that over the years, I've always said, if I really need to, if, you know, the sales drop off because it's so out of date, I would probably do it. But, you know, only if my arm was really twisted in that kind of way. But I mean, the first point is that the book is really focusing on the foundations of general relativity. And in that regard, it's not really out of date. In some sense, I lucked out by the timing of the book because, you know, the really major, well, most of the major breakthroughs that revamped the subject occurred in the 60s and early 70s. But, you know, for example, Misner, Thorne, and Wheeler was written before Hawking radiation. I had the advantage of having that development under my and everyone else's belt, and that certainly would have changed my perspective on black holes and quantum field effects enough that if I had written the book in 1972 rather than, you know, 1982 or so, you know, I might feel the need to revise it. There are certainly a lot of things that are in the book that I would do differently. When I wrote the book, I didn't think that Lagrangians were all that useful for anything in general relativity. And, you know, I've made, well, the whole line of research on, you know, phase space, another charge, black hole entropy, and so on is all really based on Lagrangian formalism. You know, so that would get, if I were to rewrite the book, that would get integrated in differently and so on. But if I think about it, the amount of work it would take to do that, well, especially the amount of work it would take to do that, the ratio of that to the improvement of the book is pretty near infinity. I mean, it's, you know, I have a treatment of Lagrangians in there that really in the appendix that really has most of the stuff I'd want. I certainly want to add another currents and charges and things like that, but it wouldn't really make a night and day difference change in the book if I were to include that. The other major obstacle that would stand between me and any desire to write a second edition is that, as people may have noticed, there have been a lot of papers published between 1984 and now. And while I do keep up with research, you know, I certainly haven't read even 1% of the papers, and you know, maybe a few percent if we only consider the top papers, and so on. And right now, none of you listening to this who've written, you know, a major breakthrough paper in the 1990s or 2000s, none of you are mad at me for not referencing your paper in my book. Okay, but that might change if I wrote a second edition. But more seriously, I mean, you know, the book is a snapshot of what was known, at least what was known by me in 1984. And even if I were to update it, the in another 5 years and certainly another 10 years, it would need more updates of that nature. And, my book wouldn't be the best place to look for the updates anyway. I mean, it wouldn't be the best place for the, latest, even if I were to write a second edition and get it completely up to date now, 5 years from now, it wouldn't be the best place to look for what's happened in LIGO. It wouldn't be the best place to look for what the current situation in cosmology is, and so on. So I'd much prefer to write, as it was mentioned, I have recently done a textbook on a new subject like electromagnetism, I mean, a different subject like electromagnetism, rather than put in an enormous amount of effort to make a minor improvement to the general relativity book. Okay, so that's those are all my questions and answers, and I'd certainly be happy to try to give more answers to other questions from anyone else.
Thank you both, David and Bob. I would like someone to raise their hands and ask questions, please. If people are shy, I could start, but I would prefer someone else. Oh, Saul.
Yeah, let me just put on my... So, Bob, thank you very much for giving us all this wonderful book. So I have a question about decisions you made as an author and sort of how you decided to do that. So one of the challenges in working with the mathematics of tensors is the terrible disorder in various conventions that people have chosen to adopt. So not just signs, but all kinds of things. So what I'm getting at is how did you make decisions? For just to take a trivial example, if you look at Christoffel symbols, right? There's one index that represents, the differentiation index, and Misner, Thorne, and Wheeler put that second at the bottom. Weinberg, who presumably got all his stuff from the 1920s books on differential geometry, put it first, and you also put it first. So I'm curious, you followed Weinberg in this example. I don't know if you did that knowingly, but there are lots of decisions like that. And how did you decide how you were going to do all this?
Yeah, okay. So, well, except for what you just mentioned, which I was not actually consciously aware of, so that's interesting. I largely followed the Misner, Thorne, and Wheeler conventions, but I had been in Chicago since 1974, and had Bob Garroch as a close colleague, and he had some fairly well-defined conventions. I mean, for example, on where you put the indices in the curvature tensor, his particular choices were kind of easy to remember, because if you do, derivative A, derivative B, dual vector C, then when you appropriately anti-symmetrize, that's Riemann ABC, and so on. So those were conventions that I was exposed to and using myself certainly since 1974 in lots of contexts. So when I was writing the book in the late 70s and then mainly in the early 80s, those kind of conventions were just on things like where to put the indices and the curvature tensor. On the metric signature, I mean, I really hated the idea of a spatial metric being negative definite. So that choice, I mean, again, I'm not agreeing with Misner, Thorne, and Wheeler conventions there. So I don't really remember having to, to kind of sit down and say, which sign should I choose for this or that.
Thank you.
Vladimir?
Uh, so first of all, I would like to say that really the book by Bob was very, very interesting, very influential, and helped to many people to understand really the basics of general relativity. But what I would like to mention is that this issue of updating, of writing the second edition would be very useful, because one thing is updating the research, the recent research, and but another thing is to correct something that possibly is wrong in the book, because one part of the book that helped me to understand that the maximal analytical extensions of the Kerr and charged Kerr spacetimes are incorrect was precisely Bob's book, because it's really very was misleading and confusing. It was difficult to understand that issue, and it took me several years with my colleague Hugo Compian to understand how this stuff should be done correctly. And so in this sense, I think it's not very good that we'll have no book by Hawking and Ellis, a new edition of that book, and now Bob is refusing to write a new edition. Even I think that Robert should do it in principle. We should stimulate him somehow, because he's very fair, honest person, and should do something for the community now, because he's still very, very young, and should improve some things. What we see that the maximum analytical extensions will be confusing for many students who are using these books like textbooks, and so they are just reading incorrect things, and somehow I think this should be I would ask Robert still to to be probably the first one to ask him to write the second edition and correct some very few things that really are needed. If he doesn't want to write about modern astrophysics and so on, no matter, but really change something which was found to be incorrect, nothing else.
Yeah. Okay. Well,
that's the suggestion. The suggestion. It's a suggestion. Really.
Yeah. So one thing I should say is, I mean, there have been errors in the book. Those are all due to David Garfinkle, by the way. A number of which were pointed out to me, shortly after within a year or so after the book came out, and others have been pointed out over the years. I mean, of course, a lot of them are kind of trivial typos, but anyway, all of the errors that I'm aware of have been corrected in subsequent printings. I mean, fortunately, the correction of all of the errors that have been found have only involved rewriting a few sentences, or doing a few things of that sort. So the book, as it, it's not up to date, but at least as far as I'm aware, it does not contain any errors or even any typos, since those of all of the ones that I was aware of have been corrected.
But I don't mean the typos. I mean the incorrect presentation of the maximum analytical extensions of Church-Kerr solution, nothing else.
Yeah. Okay. Well, if I'm not aware of something that's an outright error.
Okay, I will send you the papers. Yes.
So there's one question in the chat that I will read out, and then I see that Bernd Brugman has his hand up. The one in the chat is from PPYU. I don't know who the person is because that's all I see there. Can you talk a little bit about any influence Garrosh possibly had on your work, including this book and the Chicago School of General Relativity in general? Thank you.
Well, I mean, if I'm going to talk about it, I probably can't talk about it a little bit because he had an enormous influence. I mean, the whole style of doing things, well, doing things quite generally, but in particular, doing things in general relativity. I mean, David quoted a sentence from the preface or introduction, whatever it was, about the influence of Bob Garroch should be apparent to those people who know his viewpoints. I mean, the whole attitude of, I don't know, thinking about things geometrically, kind of not being satisfied with superficial answers, probing things much more deeply, and not being kind of satisfied with some mechanical computation that might give you the right answer, and you might be pretty confident it's giving you the right answer, but isn't giving you much understanding. Those are all very strong influences of Bob Garroch. And the use of abstract index notation is just something that naturally became part of my whole way of thinking about, well, tensors and mathematics of general relativity. I mean, through exposure to Bob, it wouldn't have, anyway, I could probably go on indefinitely, but it was absolutely enormous influence.
Thanks. Bernd?
All right. Can you hear me?
Yeah.
Bob, thank you so much for your book. I have one small anecdote for the beginning. So there I was as an exchange student, knowing nothing, knocking at doors at Syracuse University. And there was this guy, Dimitrios Christodoulou, and he said, yeah, you can have a reading class with me. Why don't you go read that book? And then we can talk about it. I had no idea what I was getting into, but the main topic, namely to do it geometrically and to connect to real mathematics, that has really stayed with me, and that was just wonderful. And if I look at the students down the hall, they are still enjoying it, so this is great. David already picked up on this little thing in your introduction where you say, well, problems aren't too hard. I think I can solve them. Do you know anybody who has solved all the problems? I checked, I made little check marks in my version of the book, how far I got. I got sort of through chapter 8, and then I gave up, and it's not even complete. Who has solved all the problems?
Well, David.
Except
No,
Jeff.
definitely not me. I've checked the equations, but as you know, some of the problems are prove this or prove that, and again, I think I can probably do them, but I haven't attempted.
Okay, yeah, well, same here.
Okay. Okay. Thanks a lot for the talk. It was wonderful.
Your Maluko?
Hello, can you hear me?
Yes.
Thank you very much for the book and for today's event. One small comment. David mentioned that Bob Garroch did not write a textbook on relativity. His 72 lecture notes have been published in 2013 by Minkowski Institute Press.
Yeah, so Bob Garroch actually wrote up lecture notes for practically every course that he taught. And he started doing that in the days before Xerox machines, and he had mimeograph lecture notes. I have a set of them, and that includes a set of lecture notes on general relativity, which probably is the basis of the book that I wasn't aware of this publication, but that probably is a version of these lecture notes from, well, those would have been written, yeah, okay, in 1972 is actually probably right. That's probably exactly right on target. So yeah, I'm in agreement with everything you've just said, although I was not aware that it was published in this and published in that nice looking form that you just held up.
Thank you.
John Carlos Santos.
Hey, Bob, great talk. I just want to say I'm a huge fan. Congratulations on 40 years of your GR book and 30 years of your quantum field theory book. I wanted to ask a question about chapter 9 specifically and how much your doctoral work influenced that, and if there was anywhere I could find your doctoral thesis.
No, I don't think there's anything in my doctoral thesis that would relate to chapters 8 or 9. That was, so that chapter 8 is causal structure, chapter 9 is singularity theorems. That was stuff I was reading a lot about as a graduate student. I mean, that was all kind of brand new, groundbreaking work, of that era. And I continued to, be very interested in that, during my postdoctoral years. But I don't think, I definitely didn't write anything in my thesis about that. And I don't think I really wrote any papers that I can think of that use that kind of machinery, before late 1970s, let's say, or early 80s. So, around the time I was writing the book. But I was reading, the Penrose and Hawking and Penrose papers and, spending a lot of time studying those.
Awesome. Thank you.
Next in line is Isvan Ratz. I hope I pronounced your name right.
Yes, I'm sorry I have no camera in my office, but thanks, Bob, for the
Oh, anyway.
And I would like to recall a memory. When I finished my PhD, it was decades ago. And at the time in Hungary, beyond the Iron Curtain, only 3 books were listed when I was preparing for the exam in general relativity: the Misner, Thorne, Wheeler, Landau, Lifshitz, and Weinberg's book. And I was in a trouble. I mean, I was trying to prepare. And at the time, I was also doing something, classifications of books in the library, and also visited, at the time we made copies in the libraries and not downloading the PDF source. So I was going to the library, and I saw a very nice cover page, which was attracting my eyes for the first time. And then I saw General Relativity as a title. So then I put all the 3 other books aside, and I learned, and I wished to go to Chicago to learn from the author of that book. I was lucky to access all these, and this means, yes, thanks a lot for the efforts you put into this writing up of this nice book. Thanks a lot. Good health.
Thank you. I see Tommaso Tirio next.
Hi, Emanuele. Hi, Bob. That's mostly thanks for writing the book. It's a great book. I have my own version of Bob Kiros's book here, just to.
That's not the one that Jorma.
Yeah, exactly. That's University of Chicago Press. So there's that book as well. I wanted to mention that.
Yeah.
And I want to share an anecdote that 2011, I was asked for the first time to teach general relativity, and I was very excited about this. So I laid out 8 different textbooks on my desk and started trying to prepare notes. I ended up basing the notes mostly on your book and Weinberg's books, exactly because of the antithesis kind of in perspectives that you mentioned earlier, kind of geometry versus field theory, kind of particle physics perspectives. So I think they're very nicely complementary. But I should also mention that I use Eric Poisson's book quite a lot whenever I couldn't remember how to derive something or some sort of technical thing. This is also great. So thanks a lot. That's all.
That's great. I don't see any other questions. I would like to ask one to Bob. David made a list of things that were not part of the book by choice. And one of the things I did not mention at all is gravitational waves. And then you have spent quite a lot of time more recently working on things like radiation reaction and so on. We had Eric at the beginning. I don't know if he's still around now, but is that something that you would have included if you were to write the book now, or what are your thoughts about this?
I guess I would really have to think carefully about whether that would be something worth including. It would probably be a pretty close call. I mean, it would certainly get referred, in chapter 4, where I'm doing linearized gravity, there's discussion of gravitational waves and, a few remarks along those lines. So it would surely get incorporated into some descriptive paragraphs there, but whether it would, whether I would find some serious section in the advanced topics or whatever, see if there's a way I could fit that in appropriately. I'd have to really give some thought to it, which if I'm not going to write a second edition, I don't actually have to give some thought to it, but it would require some thinking. However, I did incorporate that into my electromagnetism book. The last chapter there is on, self-force effects in electromagnetism.
Right. Thank you. I think if there are no other questions, we can close the meeting here. And let me remind you a couple of things. One is that we're going to post this video on YouTube. I see that Abai turned his camera on. Maybe he wants to say something else.
No, I'm just said.
Okay.
Since you
have so we're going to post a recording of the video on YouTube, and this is not going to be the last, I hope. In fact, one of the people I would like to hear from was here today. I will not spoil the surprise, but David and I will try to organize yet another event, probably in the fall at this point. So thank you for joining, and thanks, Bob, both for writing the book and for being here, and thanks to David for checking the equations and for all very many mistakes.
Okay, well, thank you very much. And yeah, I enjoyed this a lot. So thank you and bye.
And thanks for both to Bob and Emanuele for inviting me to be a part of this. It's a great honor. And thanks again, Bob, for writing this wonderful book.
Thank you all. Bye.
Take care, everyone. Bye-bye.
Mhm.